Good day and welcome to the first part of our discussion on the definite integral. The definite integral is going to be the topic of discussion for the remainder of this semester, starting off with how we can calculate it using the definition, which we'll do in this section, and then building up to some more shortcut type formulas like we encountered via differentiation, connecting this idea of the integral back to differentiation and exploring applications. So we are certainly entering an exciting portion of the course. So to begin our discussion of the definite integral, what we would like to do is build upon this previous discussion on calculating enclosed areas. So with that in mind, let me give you kind of a quick reminder. We said that a limit of the following form, the limit as n approaches infinity, and I'm going to write it out in two different formats so that we can remember the geometric significance. The first was writing it as this f of x1 delta x plus f of x2 delta x, and we're adding up a whole bunch of these, all the way up to n. That we can interpret the limit of this form as being an area under a curve. And let me add a picture here to kind of remind us of the idea. And the idea is as follows. If we have the graph of this curve, y equals f of x, and we want to know how much area is enclosed between that positive curve and the x-axis from a to b, what we did is we took that interval, we broke it up into n equally spaced subintervals, and each one has this width delta x. And in a moment I'll remind you of how we define these things. And the idea is that each of these quantities that we're adding up represents the area of a rectangle. That first quantity would be the area of a rectangle where the height is determined by the function value at x1. The second one is determined by the height at f of x2. And we do this all the way across. And the idea is a really neat one. Even though we don't have a nice geometric formula for this enclosed area, what we can do is approximate it as closely as we would like by using enough of these rectangles. And we can make it exact by taking the limit as n goes to infinity. And we saw it's much more convenient to express this as the limit and then converting it over into sigma notation. The sum from I equals 1 to n of f of x sub I delta x. And it turns out that this idea is precisely how we define the definite integral as well. For the definite integral, we do have to make some assumptions that we have a continuous function. And what we do is we proceed as we did before. We divide the interval into n subintervals of equal width. This delta x is b minus a over n, a formula we have to make sure that we recall. And then we have these endpoints of the intervals as we've seen above, the x1, x2, all the way up through xn. And the formula that one can use to get those is the same formula we introduced previously. X sub I is a plus I delta x. That is to say, geometrically, x sub I is the right-hand endpoint of the ith subinterval. You start at a and you travel across I subintervals. With this in mind, the definite integral of f from x equals a to x equals b is defined as follows. The notation we have would be integral symbol from a to b, which I would read as the definite integral from a to b, of the function f of x. This is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. And wow, that looks awfully familiar. We're defining this precisely as we've defined this idea of an enclosed area previously. The big difference is we don't have an assumption that the function is going to be purely positive, so we'll have to think through how we interpret that. But before getting carried away, let's go ahead and just talk a bit about the notation and introduce some corresponding language. So as I mentioned, this funny extended squiggly s, we refer to this as being an integral sign or integral symbol. The function f of x, which we are integrating in this case, we refer to this as being the integrand. And the dx is telling us what variable to integrate with respect to. And in Calculus 1, it's not really as big of a concern. It's more of a notational thing telling us the integral symbol is where to start integrating. When we hit the dx, that tells us to stop integrating. When you get into some future calculus courses, you'll have functions with more than one variable, and we'll have to be a bit more careful with that. But for now, it's just part of the notation. Then let me note in particular the a and the b that we see. We refer to those as being the limits of integration, where in particular we call the a the lower limit and b the upper limit. So just trying to make sure we're all on the same page in terms of notation and terminology. Furthermore, this sum that we are taking the limit of is something that we've seen appear frequently throughout the last section, and we certainly will throughout our next several videos as well. So we're going to go ahead and give this a name. This is something that is referred to as being a Riemann sum. And now working our way back to this interpretation that we previously discussed, note if the function is purely positive, then we're in the same exact scenario that we were previously. So just to kind of give you that quick reminder, even though I know we already have a picture, but if we have the graph of y equals f of x, and we are interested in how much area is enclosed underneath that positive curve and in between the x-axes from a to b, call this area A, that is what the definite integral is going to calculate for us. The definite integral for a positive function is interpreted as the area under the curve so that would be the graph of y equals f of x, and above the x-axis between x equals a to x equals b. Now maybe the more interesting thing for us to think about is what if the function f that we're thinking about and we're considering graphically happens to be both negative and positive? Then how do we interpret this? And let me go ahead and just draw a simple picture to maybe assist the discussion. So maybe we have the graph of a curve that looks something like this. And we're interested in evaluating the definite integral of this function f from a to b. Well, how we are going to interpret this is as follows. We're going to note that there's, in a sense, two distinct areas enclosed. There's A1, an area enclosed above the x-axis by the curve. And then there's a second area, call it A2, enclosed below the x-axis for the curve. And we're going to interpret the definite integral as being a net difference of enclosed areas. You take the area enclosed above the x-axis, and you subtract away the area enclosed below. Now note when we're talking about areas, areas will never be negative. But what we will do is assign a negative, or we will subtract away the area enclosed underneath that x-axis. And just to give you an idea of where this comes into play, when we are looking at the definition of the definite integral, it involves these Riemann sums, where we're adding up the areas of rectangles. And in terms of this region A2, when we start drawing in some of these rectangles, the quantity or the expression that we're using to determine their height is f of x sub I delta x. But the f of x sub I, in that case, is a negative quantity, and that negative is the reason we're subtracting away the area enclosed underneath the x-axis. So that's hopefully the intuition. The phrase you will hear me say frequently is that a definite integral calculates a net difference of enclosed areas. That is the area enclosed above the x-axis, and we subtract away, i.e. the difference here, the area enclosed below the x-axis. And I think we could actually visualize this by looking at a nice concrete example. So I'm just going to kind of add this example to the bottom of our first page of the note packet. So something that we can now calculate using this interpretation is the definite integral from 0 to pi of cosine. So recall, we're saying 0 is our lower limit of integration, pi is our upper limit of integration. The function cosine is what we refer to as being the integrand function. And let's just think about what this would look like graphically. And it's essentially the same picture that we have drawn a moment ago. The cosine curve from 0 to pi, it starts off being 1 at 0. At pi over 2, cosine is 0, and at pi, cosine is minus 1. So roughly speaking, something along these lines. So the value of this definite integral is going to be similar to our above observation, a1 minus a2, where in this case, a1 is this area enclosed above the x-axis, and a2 is this area enclosed below. And by the symmetry of this cosine curve, the area A1 and the area A2 are, in fact, equal to each other. And since A1 is equal to A2, the value of this definite integral is equal to 0. And remember, the language we would use, we wouldn't say that the cosine curve encloses 0 area between itself and the x-axis. That statement's not correct. There's all kinds of area enclosed. The correct statement would be that the net difference of enclosed areas is 0. The area enclosed above the x-axis is equal to the area enclosed below the x-axis. This completes our introduction into the definite integral and its interpretation. We will continue this discussion in our next video by evaluating the definite integral and see the similarities to our previous discussion with enclosed areas. So stay tuned and take care.